Hi everyone. So now I'm going to talk about a couple of case studies on explainable AI. One from my time at Google, and the other one from Fiddler Labs. So the first case study is on applying integrated gradients for explaining diabetic retinopathy predictions. So diabetic retinopathy is a complication of diabetes that affects the eyes. In its most severe form, it can cause blindness. So diabetic retinopathy has sort of five levels. It's none, mild, moderate, severe, and proliferative. And proliferative DR is vision threatening. So uh, wha- so now a team at Google uh, had trained a deep neural network to make diabetic retinopathy predictions achieves uh, that beats the state of the art in any automated prediction of DR. It achieves an AUC of 0.97. So this model was sort of a big deal. So this case study was about, can we use explainability to further offer explanations for how the model reasons. In particular, can we offer explanations to assist the doctor? So for instance, this image on the screen over here is labeled as proliferative DR. So can we provide an explanation for why the model thinks it's proliferative? So we apply the integrated gradients method, and as before, we highlight the pixels that receive the highest attribution. So here we basically visualize the attributions by by scaling them on the green channel and placing them on a gray background image, grayscale background image. So these pixels that are marked in green are the ones that are most important for this prediction. So here it turns out that the model and the attributions catch very meaningful patterns. So these green regions outside the optic disc are essentially lesions, and what the model is catching inside the optic disc is neovascularization, uh, which are these tiny blood vessels that are hard to see for the naked eye, but the model catches them. And the presence of these blood vessels is a strong indicator of proliferative DR. Uh, so it's good that the model is able to catch that, and the attributions are able to surface that. So now we'd like to see if these attributions can really help doctor better diagnose diabetic retinopathy. So for this, we ran a clinical study with 9 doctors grading 2,000 images. So the study had 3 arms. So in the first arm, the doctor was just shown the image, and they were asked to provide a DR prediction. In the second arm, they were shown the image and the model's prediction. What does the model predict? And now the doctor was asked to provide his or her prediction. And in the third arm, the doctor was shown the image, the model's prediction, and the explanation from integrated gradients. And again, the doctor was asked to score the image. So the findings are very interesting. So the first finding we had is that experimental arm B does significantly better than A, which means seeing the model's prediction really improves the doctor's accuracy versus just the doctor grading the image by themselves. Now, both B experimental arms B and C pro- increase the doctor's accuracy compared to A. But the marginal increase of explanations over seeing the predictions is not that much. So what we found is that explanations improve the accuracy for some cases, but they also hurt the accuracy on many other cases. In particular, the cases where seeing the explanation hurt the doctor's performance were ones where the ground truth label was mild DR, sorry, none DR, but the model predicted it as mild. So the model was wrong where it predicted mild form of the disease, whereas the image had no disease. Now the attributions are all for the model's prediction, right? The attributions are explaining why did the model predict this. So they were all corresponding to the mild prediction label. And so some parts of the image got highlighted, and this often confused doctors, wherein they would look at the attributions and then go like, oh, maybe the network is catching something that I'm not able to see, so perhaps this is mild DR. So they would go with the model, and therefore their accuracy would hurt. Whereas when they saw that same image without any assistant, they would have labeled it as none. Uh, we also found that both in experimental arms B and C, the doctor model agreement increased. So the doctor's predictions were more aligned with the model's prediction. So this is actually a form of over reliance, which has been studied quite heavily in this automation bias literature. There is prior evidence that whenever humans deal with an automated system, there is this risk of overly relying on that system, where we turn blind to sort of reasoning about events ourselves versus relying on the system to make all the decisions for us. So this is we saw sort of aspects of that in this study as well. Uh, the results are published in a Journal of Ophthalmology paper from 2018. The second case study I'd like to walk you through is what we are building at Fiddler Labs. So, in a nutshell, what we are building is an explainable AI engine. The mission of the company is to unlock trust, visibility, and insights for any machine learning model out there. So, what this explainable AI engine is, it's a platform where you can bring your data, you bring your model, and out comes explanations like this. So here's an example of an explanation from Fiddler. So this is an explanation of a credit lending model. It's explaining an individual prediction made by that model. So this box in red at the top left of the page is essentially the prediction for that particular input. So in this case, the prediction is 0.3. On the left rail over here, you see all the features of the input, and this tornado chart on the right are the Shapley value attributions. So this picture is telling us that FICO, the feature FICO, is the most important for this model, whereas zip code and school are negative for this credit risk prediction. This is an interesting finding, whereas one would not expect the college that the applicant went to matter for their credit risk prediction. Now, it turns out that this particular college is Salem College, which is a women's only college. So the model is internally using school as a proxy for gender. And this is something that attributions helped us catch. The other thing this page allows you to do is you can probe the same model on counterfactual inputs. So these, you can see on the left rail we have sliders underneath every feature. So you can vary the slider and then see how the prediction changes. So I can move the FICO from 790 to 800 or to 750 and then see what the impact on the prediction is. So you can sort of do what if analysis or scenario analysis using the same interface. We also have this entire explanation available as an API that you can plug into your own case management system. So perhaps a bank or a loan officer at a bank who's going through these credit applications would also have other metadata that he or she would look at in sort of making the final decision. So as part of your case analysis tool, you can sort of plug in explanations from Fiddler as one more sort of piece of evidence for a particular application. And that will help the loan officer sort of make a better decision on whether to approve or deny the request. A second feature offered by the platform is slice and explain. So this is a step towards global explanations of a model. So what we are doing here is we are blending traditional SQL analysis of data sets with model attribution, with prediction attribution. So what you can do is you can write SQL queries through this interface to capture slices of the data. Let's say you can say, show me the slice of all males or all applications from California. So what you get is a slice, which is a set of points, and now you can explain this slice. And we offer many different flavors of explanation. So of course, you can go to individual points in the slice and then look at attributions for them, which is this screen on the right-hand side of the page. This is an attribution for this first point over here. But then you can also look at aggregate attribution. So we show you a tornado chart of the average attribution across all of these points. You can look at how the features are distributed for a particular slice, how the features are correlated with the target, partial dependence plots of how the target varies as each of these features varies on this particular slice. So it's sort of a drill down style analysis where we are blending typical data drill down, where you are slicing and dicing a data set, with explainability, where you can sort of slice in light of the explanations. A third feature of the platform is monitoring. So here you can route your live traffic. So you can serve your model anywhere, but you can route your live traffic to Fiddler. And then what Fiddler can offer you is it can tell you whether the features that the model is facing in real time, are they drifting relative to the training distribution. Or it can also help you catch outliers. Are there egregious predictions, really high or really low prediction that the model is making in real time. Whenever those kind of predictions happen, then you can go back to the explainability interface and explain them. So if there is a very low prediction that was made, you can click this explain button and then go back to that interface with the tornado chart and the what if sliders, and you can sort of probe the model and see why did it make that egregious prediction. The vision of the company and the where we want to take this entire platform is sort of captured in this flywheel. So what we'd ideally like to do is embed explainability in all parts of the AI lifecycle. So we want explainability during training to enable model debugging, model visualization, feature selection, feature engineering, and so on. We'd like explainability at QA time to check whether the model is complying with various regulations. Then you want explainability at the time of prediction so that you have explanations coming for individual predictions that you may want to then surface to the relevant stakeholders, in some cases even to the end user. Then you want explainability during monitoring so that you can monitor what inputs the model is seeing, what predictions it's making, why are the predictions sort of, if they are diverging from what you have seen during the training distribution or from a previous time window, then why are they diverging? If there are outliers, then why are they happening, and so on. And then finally, we want to root cause these issues and then feed them back into the training to continuously improve the model. That's sort of the holy grail of explainability on how do we take insights from explanations back to the model to improve it in an automated manner. So that's sort of the large open problem here that we are aiming to tackle. Thank you.